Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. Before introducing our seminar speaker, a few housekeeping announcements. Today's event is entirely online, so all interactions will be via Zoom. Use the Q&A button at the bottom of the Zoom screen to enter questions throughout the event. Questions will be answered at the end of the presentation, and at that time, you can raise your hand in Zoom as well, and our moderators will unmute you so you can ask your question. Along with all previous Deeper Talks, this talk will be recorded and available to view online at theinstitute.surf/deepertalks, as well as on our YouTube and Vimeo channels. Now it's my privilege to introduce today's speaker. Dr. Ian Gwynn is a neutrino physicist at Oak Ridge National Laboratory. He's an experimentalist who studies the properties of neutrinos and is interested in the nature of neutrino mass and the origin of matter in the universe. He received his PhD from the University of Washington in 2019, worked as a postdoc at the University of North Carolina at Chapel Hill, and then began at ORNL in 2023. Dr. Gwynn is involved in the search for neutrinoless double beta decay in germanium detectors, with the Majorana demonstrator, for which he serves as the analysis coordinator, and with Legend, for which he serves as the pulse shape analysis lead. Dr. Gwynn spent a great amount of time at SURF between the years of 2014 and 2019, where he helped construct, characterize, and operate the Majorana demonstrator. We at SURF remember Dr. Gwynn's time underground at our facility, and I welcome the audience to get set to hear about the final results from 1 decade of operating the Majorana demonstrator. Take it away, Ian.
For the introduction. So are my slides showing up? Okay, yeah, I can see it now. Great. So I'm Ian. As Jared just said, I'll be talking about the results from 1 full decade of operating Majorana. Let's see. There we go. All right, so I'll start with just a really quick overview of what I'm going to talk about. I'll start by talking about neutrinos and neutrinoless double beta decay and sort of motivating this search. Then I'll talk about the Majorana demonstrator itself and how it works, how we built it, and what the sort of final result of the neutrinoless double beta decay search was. Then I'll talk about our broader physics program and some recent results from the last year or so, searching for other exotic types of physics, or some maybe not so exotic, but still very interesting. And then I'll end with a sort of future outlook and conclusion. So let's start with neutrinos. So neutrinos are often called ghost particles. The reason for that is they're invisible and they basically just fly through everything. So one of my favorite fun facts about neutrinos is that in any given second, 1 trillion pass through your thumb, and yet during your entire life, the odds are less than 1 will interact with your entire body. So they don't do that much. That makes them really hard to study, but in spite of that, we still know quite a bit about them. So we know that they're electrically neutral. This is why they don't interact with anything, but they do interact with the weak force, where the sort of classic example of a weak interaction is beta decay, which I'm showing right here, which turns a neutron into a proton, an electron, and an antineutrino. So based on what we've been able to learn, we have fitted neutrinos into the standard model of particle physics, which I'm showing over here on the right. So the standard model includes quarks, which are the purple particles up here. They make up protons and neutrons. Leptons on the bottom here include neutrinos, which are the neutral leptons, and electrons and their sort of heavier relatives, the muon and tau particles, which are charged leptons, and the force carriers over here. So there's 3 flavors of the spin 1/2 particles. So the 3 flavors of neutrinos correspond to which flavor of charged lepton they interact with. And all of the interactions that we've ever observed with a weak force conserve something called lepton number, which means that if you create a neutrino, you have to create either an anti-neutrino or an anti-electron or other charged lepton to go along with it. And we've never seen this be broken before. And the last thing I'll bring up about neutrinos right now is that since the weak force is maximally parity violating, it only interacts with left-handed neutrinos or right-handed antineutrinos. The result of this is actually that the standard model of particle physics only includes the left-handed neutrino spinner, and one corollary of this is that the neutrinos are massless in the standard model. Um, one really interesting, anomaly that was discovered starting in 1970 at Homestake Mine before it became SURF is what's called the solar neutrino problem. So Ray Davis built a giant detector to look for solar neutrinos, and he actually saw solar neutrinos. However, a theorist named John Bacall predicted the number of solar neutrinos we'd see based on the amount of fusion happening in the core of the sun. And it turned out that Ray Davis saw only about a third as many neutrinos as expected. This ended up being confirmed by some other experiments and came to be known as the solar neutrino problem. This was ultimately solved in the late 90s by two experiments, Super Kamiokande and the Sudbury Neutrino Observatory. And what they did is prove that neutrinos do something called oscillation, where as they travel through space, the different flavors of neutrino will morph from one flavor into another flavor. This is something that turns out to only be possible if neutrinos have mass. And that actually means that this violates the standard model. So we're doing what's called beyond the standard model of physics, and that means we need to add something to the standard model to incorporate neutrino mass. That could be as simple as a right-handed partner to the neutrino, but something has to be added. So there are two main ways that we can give mass to neutrinos. The first is called the Dirac mechanism. So in the 20s, when Paul Dirac was postulating relativistic quantum mechanics, he found that mass would come from coupling a left-handed particle to a right-handed particle. He also made a really interesting prediction, which is that antimatter would exist, and this was actually something that got discovered a few years later. So basically, antimatter is a distinct particle from matter that has the opposite charge, and when matter and antimatter meet, they do something called annihilation, where they, force each other out of existence. So the Dirac mechanism is how all of the other fundamental particles get their mass, and this is modulated by the Higgs boson. The other mechanism was postulated by Ettore Majorana in the early 30s. So Majorana said you could also get mass by coupling the left-handed particle to its charge conjugate, which is the right-handed antiparticle. And another way that we often express this when we talk about this is we say that particle is its own antiparticle. And the reason for that is this actually allows the particle to annihilate itself. This is only possible for neutral spin one-half particles. That means that of all of the fundamental particles, the neutrino is the only particle that could possibly be Majorana. And it would enable processes that violate that conservation of lepton number. That's very exciting because that would help to answer one of the biggest mysteries in the universe. So I think we can all agree that there's a lot of stuff in the universe. So if you look out into space, you see, a whole lot of light. We exist, so you're interacting with, baryonic matter every day. Um, Believe it or not, though, that's very surprising to physicists. So if you sort of naively follow the Big Bang theory, you expect to produce equal amounts of matter and antimatter in the early universe, and then shortly thereafter, you expect the matter and antimatter to annihilate. So based on the standard model processes, we actually see about 1 billion times as much matter in the universe as we would expect based on that sort of naive interpretation. So a guy named Andrei Sakharov came up with the conditions needed to produce all of the matter we see. One of the key ones is the existence of a process that produces matter without producing antimatter. In other words, either lepton or baryon number violation. So discovering Majorana mass, which would enable lepton number violation, would be very exciting because this could help us answer this mystery by enabling a process called leptogenesis. So the next question is, how do we actually prove whether or not the neutrino is a Majorana particle? And we do that using double beta decay. So double beta decay is exactly what it sounds like. It's two beta decays happening at the same time, which produces two electrons, two antineutrinos, and turns two neutrons into two protons. This conserves all of the same conservation laws as normal beta decay, so it conserves energy and momentum. One of the results of this is since the neutrino actually carries some energy out of the detector, you don't observe all of the energy, so you see a broad energy spectrum, and it conserves lepton number. This has been seen before. This isn't something, terribly unexpected. It's been seen in 12 different isotopes with very long half-lives on the order of a billion times the age of the universe. What we're really interested in is a different process called neutrinoless double beta decay, where you have the two beta decays, but you don't get the two antineutrinos. And the result of the missing neutrinos is that we're going to violate lepton number by producing two leptons in the electrons and no balancing antineutrinos. This is something that can happen if the neutrino does this right here, where there's sort of two ways to interpret this. One is you can say the neutrino is annihilating itself, or the two neutrinos are annihilating themselves. Or another way is to sort of say that you have this loop where the neutrino is being absorbed in one decay and emitted in the other. But in any case, you're getting this violation. We do still expect to conserve energy, and since there's no neutrinos to carry away the energy, we would observe monoenergetic peak, and I'll show that in a few slides. This has never been seen before, but the current half-life limits are on the order of a million billion times the age of the universe. So the discovery, the key thing here is that discovery of neutrinoless double beta decay would prove that neutrinos are Majorana particles. So the very long half-life of the decay is governed by a few things. So first there is the phase space factor. This is something that can be very well calculated. The next is the nuclear matrix element. This is basically accounting for the structure of the protons and neutrons in a nucleus, and is very, very, very hard to calculate. So theorists have been working on this for a long time, and there's a lot of uncertainty right now with factors of 3 difference based on what method is used. There's actually been a ton of recent progress, and I think we're all really excited to see where that goes in the next few years. And then the last factor is called the effective Majorana mass, or M beta beta, which is this green one here. That's based on the mass of the neutrino, and based on what we've already measured, we can constrain what possible values that can have, and that's what this is shown here. So this is, actually, I'll go to the next slide, which has a bigger version of this. So this is what M beta beta can be as a function of the lightest neutrino mass, and it can fall in either of these two bands here. So there are many experiments searching for neutrinoless double beta decay in many isotopes. Currently, the best overall limit is in xenon 136 from an experiment in Japan called Camlan-Zen. The best experiment in germanium is from an experiment called Gerda. And both of these have half-lives in excess of 10 to the 26 years. The sort of medium-term goal for the community is to hit this red line here, which covers the orange region, which is known as the inverted ordering band. That requires an M beta beta limit of less than 18 millielectron volts, or a half-life sensitivity of greater than 10 to the 28 years for germanium, which is a billion times the age of the universe. So, that is very challenging because this is a very long half-life. So we benefit a lot from basically Avogadro's number, the fact that we can get a lot of nuclei in, a relatively normal amount of material. But even in spite of that, with a half-life of 10 to the 28 years, we're talking about, one decay in a ton of material every 2 years. So this means we need a very large experiment uh, that can search for a long time. The signature we're going to look at is shown here. So what I'm showing here is the 2-neutrino double beta decay spectrum in green. This is a broad spectral feature, as I mentioned before. And then a peak at the end of this at what's called Q beta beta in blue here. And that's what our signature is going to be. So the fact that it has this very clear peak is actually very nice for us. Um, but because we need to observe so few events in order to get the sensitivity we require, we really need to build a very low background experiment. So what this is showing here is the discovery sensitivity for a double beta decay experiment as a function of exposure. So in order to sort of reach this goal the community has set, we want to get about 10 ton years of exposure, which could be achieved by watching 1 ton for 10 years, or equivalently 10 tons for 1 year, but we're going to go with the 1 ton for 10 years option. And we need extremely low backgrounds because as soon as you introduce possible background processes, it really affects your sensitivity quite a bit. So our goal is to build basically a background-free experiment. The question is, how do you build such an experiment? There are a lot of different ideas out there, searching through a variety of different isotopes. But what a lot of these experiments have, at least a few of these things in common. So we typically want the source of the decay to be the detector, so that we have a very high detection efficiency. We want a very good energy resolution, so we have a very clear peak that we can search for. We want as few background sources as possible, which requires a very clean experiment. And if possible, we want some way through our data analysis to separate out the signal-like events from the background-like events. So germanium-76 is one of the isotopes that does double beta decay, and that's what I'm going to talk about for the rest of this. Germanium actually has a very long history of searching for double beta decay, going all the way back to the 60s. And in that time, so germanium detectors are what we use for this, high purity germanium detectors. Germanium detectors are very commonly used in radiation detection, so they're an extremely well understood technology. The manufacturing process is very clean. They have excellent energy resolution. In fact, that energy resolution is why we love them as radiation detectors. Some of the newer technologies enable pulse shape discrimination of signals from backgrounds, and we can enrich the germanium very highly in the decay isotope to do this search. So here you're seeing the half-life limits as a function of a year for neutrinoless double beta decay. And down here, you're seeing some photos from a few experiments. So Majorana demonstrator is, of course, what I'm going to be talking about. Gerda was operating at the same time as Majorana. And as I mentioned a few slides ago, that actually currently holds the leading limit for germanium. Legend 200 is already up and operating. This is a combination of Majorana and Gerda experiments that is going to sort of carry the torch forward. And I'll talk about that right at the very end. Now I'm going to go into talking about the Majorana demonstrator. So Majorana is, of course, searching for neutrinoless double beta decay in germanium-76 using high purity germanium detectors. So these are what these germanium detectors look like. Each detector is around a kilogram in mass, maybe a few kilograms for some of these really big ones. In order to get the large amount of mass we require, then we build an array of detectors, which is what you're seeing here. So the Majorana demonstrator had 30 kilograms of detectors that were enriched to 88% in germanium-76 and 14 kilograms of detectors at the natural isotopic abundance of about 7 or 8%. In order to achieve a very low background, the arrays of detectors were placed inside of this giant lead shield that you can see here, and here's sort of a drawing of what that looks like. So the shielding had a layer of very clean copper shielding, followed by lead, and then outside of that, it has some plastics and muon veto panels as well. The experiment operated at the Sanford Underground Research Facility, and it's actually still operating today, doing a different physics search, which I'll talk about later, and ultimately reached an exposure of 65 kilogram years. So this is the full collaboration right here. We are an international collaboration, mostly located in the United States. Here's a photo of us at our last collaboration meeting. So this is actually a few years old now. And now I'll get into some more detail. So this is sort of the full operating history of the Majorana demonstrator. The experiment first went online over 10 years ago now in 2014 when we installed Module 1. So I should also be clear that we actually had two separate arrays of detectors housed in separate vacuum cryostats, and these are what I refer to as modules here. So the first module operated from 2014 to 2021, almost continuously in that time. There were only a few breaks. Module 2 was first deployed about 6 months later in 2015. And then we actually pulled it out for an upgrade where we installed some of these larger detectors here. And also, we tested out some new cables and electronics as well. That operated for about a year before we removed both modules. At this point, we sent all of our enriched detectors to Italy for inclusion in the Legend experiment, and then restarted Module 2 with some of the natural isotopic abundance detectors. We use this to do some background studies and to search for the decay of tantalum 180 metastable state, which I'll describe that a little bit later. So this is another way of looking at the operating history of Majorana. So this is the exposure as a function of time up until we removed the enriched detectors here. So we got 65 kilogram years of exposure. This is what was published in our final limit here. And as you can see, we were almost continuously collecting exposure. There were only a few breaks during this entire time. Okay. So Majorana demonstrator, of course, as I've said, we need to make sure that we're a background-free experiment. This is sort of a summary of the backgrounds that we worry about the most, although there are a few others. So we worry about gamma rays, which can be emitted from the environment. So this can come from primordial isotopes like uranium and thorium, or from cosmogenically activated ones like cobalt. We worry about cosmic rays from the atmosphere and some of the particles they can produce. We worry about cosmogenically activated nuclei inside of the detector, and we worry about surface events from alphas and betas from radon daughters that can plate onto the surfaces of detectors. We do have strategies for mitigating all of these, which I'll describe now. Let's see. The first thing we do is locate our experiment underground. So this is why we housed it at SURF. So we were at the 50-foot level, right next door to the LZ experiment, which is where the Davis experiment was done. Here you can see a few photos of the lab. So this is sort of the outside of the lab, and here you can see some from inside. This is a nice panoramic view and a single very busy graduate student. Um, Next, we worry a lot about the radio purity of the materials we use to build the experiment. So I think the most well-known example of this is going to be our electroformed copper, which we chemically grow underground at SURF. We clean it as much as possible. We machine all of our parts out of this copper. There's actually an underground machine shop that is responsible for all of these, a single machinist named Randy. Um, we've we use these parts, which we use very low mass designs to minimize the amount of this copper near them, to support the array of detectors, which you can see what that looks like here. And we do all of this as much as possible in nitrogen purged environments in order to avoid radon exposure. We also try to avoid letting the copper go to the surface to avoid cosmogenic activation. So the detectors we use are called p-type point contact detectors. That refers to the fact that the p plus contact of the detector is just this little point right here, while the n plus is the outside surfaces. This geometry for the detector has a few advantages. So first of all, it has excellent energy resolution. And second of all, it has this property where so as you watch this here, as the charge approaches the point contact, it rises very, very slowly until it gets very close, where you get this really fast sudden rise. So the signal, because of this really sharp rise, the signal actually has a shape that varies a lot based on the position in the detector. And this has some big advantages for us that I'll describe in a couple of slides. So we use three different types of detectors. So the two that we used for most of the time were the PPCs and veggie detectors, which both have mass of around a kilogram or less. But there are actually big advantages to having larger detectors in terms of getting a low background experiment. So one sort of R&D product during the lifetime of Majorana was the production of these new inverted coaxial point contact detectors, which are much larger, up to 4 kilograms. And we included a few of these for a period of our run as well. So as I said, the experiment has excellent energy resolution. The demonstrator actually had the best energy resolution of any of the experiments performed to date at 0.12%. We were able to accomplish this thanks, first of all, to the intrinsically good energy resolution of the detectors. We also used novel techniques such as an ADC nonlinearity correction and a charge trapping correction for these detectors that managed to get us to this extremely good level. This here is showing a calibration spectrum. So we calibrated using a thorium-228 line source, which was inserted and wound around the cryostats like this. So here you can see the full width half max of these peaks as a function of energy, and you can see how sharp these peaks look up here. So now we'll talk a bit about some of the pulse shape discrimination we can do to separate signal events from background events. So the first thing we do is try to separate single site events from multi-site events. So double beta decay, all of the energy from the two electrons is absorbed within about a millimeter of the site of the decay. We call that a single site event, whereas a lot of gamma rays will scatter from one point in the detector to another, and we call that a multi-site event. So because of this sort of the fact that we can localize sites in the events because of this sharp rise that I described a few slides ago, the multi-site events actually then produce this pulse that has multiple distinct rises like this. And so we can look for pulses that look like that by using a parameter we call A versus E, which is comparing the maximum current amplitude to the total energy of the event. And so the multi-site events have a lower amplitude, and therefore we can reject them based on that. And here you can see the result of that rejection. So the double escape peak, or DEP, here is an intrinsically single site event, and we keep about 90% of those when using A versus E. The bismuth gamma here is about 90 to 95% multi-site, and we reject almost all of them. The other big event population that we target is surface events. Radon daughters on the surfaces can dump alphas and betas right into them. And depending on where on the surfaces these particles are deposited, you get different shapes of waveforms that can be recognized. So events very close to the point contact produce a very, very sharp rise that we can actually recognize using the same A over E cut that I just described. And then events on the passivated and N plus surfaces tend to produce slow components like this. And this is an interesting waveform because it actually exhibits all of the things we can look for. But some of the events will have a slow component on the order of like 10 microseconds. Some of them will have a slow component on the order of 1 microsecond. So we have two different cuts called DCR and LQ that can target those. So based on all of this that I've shown, this is sort of our final result. So this is 65 kilogram years of exposure, and this is the full energy spectrum after our data cleaning and muon veto cuts. So you can see the effect of the cuts going from the dark gray to the light gray here. You can see the surface cuts, which get rid of the majority of our events, and then you can see the result of the multi-site cut, which gets rid of about half of the remaining events. The by far dominant feature of this spectrum, we are very happy to say, is this two neutrino double beta decay shape right here. And then we are looking for neutrinoless double beta decay at 2039 keV in this little window right here. So the background index was measured using the events around here to be 16 counts per pole with half max ton year. This is the second lowest background index of any of the neutrinoless double beta decay searches to date, which we're very proud of. So based on this, we were able to produce a final result. We expected 1.5 background counts in our region of interest. We measured 1. This allowed us to create a limit of 8.3 times 10 to the 25 years, which corresponds to an M beta beta of less than 113 to 269 millielectron volts, depending on your choice of nuclear matrix element. And here you can see how that falls on the M beta beta phase space. You'll note this is a linear plot instead of a log plot, which is why it looks a little different, but it's the same plot otherwise. And you can see a comparison to some of the other experiments. We're actually not done with this data. We're actually going to combine this data with data taken by Gerda and Legend 200 to produce a combined limit very soon. So in addition, we really want to understand where our backgrounds are coming from. And to do that, we build a background model by fitting out a very large number of possible background components to our data. So we actually had 110 different combinations of hardware component groups and isotopes that we fitted to our data. And we ended up finding, so one of the questions we wanted to answer is why we had as much background as we did. So that 16 counts per full half max kilogram ton year was higher than we expected. And we were able to locate most of that excess to a single component above module 1, which this is part of the cooling system for the experiment. And we actually find that over half of the events from module 1 were coming from this hotspot. So that's the light green here. One very exciting aspect of this background model is we're also able to use this to get a physics result, which is the half-life of 2 neutrino double beta decay. Since it's a broad spectral feature, we need a full background model in order to properly do background subtraction. So here you can see the same model, except this time it's a wider energy range, and you're seeing it separated out by isotope rather than hardware components. The orange here is the 2 neutrino, and we measure a half-life of about 2 times 10 to the 21 years. This is still preliminary. We're still making sure that we're fully confident in the uncertainties we report, but this should be published fairly soon. This is also consistent with previous measurements. All right, so that's the Majorana demonstrators neutrinoless double beta decay program. For the rest of the talk, I'll talk, I guess I'm long because of the gap there. So stop me if I'm going too long. But I'll talk about our broader physics program where we looked for some other physics processes. So the Majorana demonstrator, because of its extremely low backgrounds, its very good energy resolution, and its low energy thresholds, and the fact that it had an array of detectors, which is useful for certain types of events, was actually able to perform very sensitive searches to a wide variety of exotic and less exotic physics processes. We are still in the process of doing some of these analyses, but I'll discuss a few of them to wrap up this talk. So I'll start with double beta decay to excited states. I'm actually going to spend a little more time with this one than the others because this is an analysis that I led. But germanium-76 can decay into 3 different excited states of selenium-76. These decays are going to be characterized by a double beta decay followed promptly by the emission of 1 or 2 gamma rays that can then fly to another site in the detector and interact. So this is an intrinsically multi-site event. There are 3 different excited states, but the decay can be either neutrinoless or 2 neutrino. So there are actually 6 different decay modes that we can look for. I'm going to be focusing on the decay to the first 0+ excited state here because this one was actually, there was a realistic chance of detection here. So the detection signature we're going to focus on is a peak, a gamma ray peak corresponding to when the gamma goes from one detector to another and is fully absorbed. Because there's multiple detectors involved, we're going to only look at events including multiple detectors. So here I'm showing a simulation of this decay. This is multiplicity 2 events with the higher energy on the x-axis and the lower energy on the y-axis. And this bright line here is what we're going to be looking for. So because there are two detectors, there are multiple observables that we can use to improve the sensitivity. So we can use the energy in the second detector. We can ask if the second detector was an enriched detector. We can use our pulse shape discrimination for multi-site gammas, and we can use what we know about that hotspot to avoid detectors nearby. So here what I'm showing is how we use the energy in the second detector. So what we can do is we can reject events with either some energies or coincident energies near known gammas. So the sum energies look like these. This would happen if a gamma ray scatters in one detector and then leaves the rest of its energy in a second detector. That's these diagonal lines. And the coincident energy would be if you have a gamma ray cascade where one of the gammas is fully absorbed. And that's these vertical and horizontal lines. And then the signal is the orange line here, although it doesn't, depending on your screen, it doesn't always look that clearly different from the red. Um, but we were able to develop an algorithm that was sort of automatically able to select these energy ranges to reject in order to optimize our sensitivity. So this is then what the final analysis looks like. So we use this most of the same data as the neutrino double beta decay. You'll notice that I list 98 kilogram years instead of 65. The reason for that is that we account for the exposure a little bit differently for this search than the other one. But based on this, Majorana was able to set the most sensitive limit to date for the first 0 plus excited state decay as well as all of the others. So for that one, it was 1.5 times 10 to the 24 years. So this is all of the multiplicity 2 data, and this little line here, we project into one dimension along this axis here in order to get this histogram here. So this includes all of the events in the high multiplicity events. And then you can see the effect of the different cuts I described on the previous slide, which reject 90% of the events, leaving us with this. And then we can search for the two peaks at 559 and 563 keV here. And we did the same thing, more or less, for all 6 of the decay modes and set world-leading limits in all of them. Here you can see why I talked more about the first 0 plus excited state decay, which is that the limit we were able to set is actually in a very interesting range of values, which is to say the values predicted by theory. So based on which nuclear matrix element technique you use, you actually might have predicted we would have seen something. So we actually ruled out all of the predictions made using the quasi-random phase approximation. And our sensitivity is actually in an interesting range for some of the others as well. So now I'll move on to some tests of fundamental quantum mechanics that we were able to do. So we were able to test charge conservation and the Pauli exclusion principle by turning them into peak searches and looking for atomic de-excitations caused by these. So in charge non-conservation, we're looking for an electron in the inner atomic shell to basically pop and produce 3 neutrinos, and then the de-excitation should produce a peak right here. And we were able to set a world-leading limit for electron decay of 2.8 times 10 to the 25 years. Pauli exclusion principle theorists have come up with some different ways this could happen that they characterize into 3 different types, and we looked for 2 of them. So type 3 is when an electron inside of the atom basically just falls into the innermost shell along with the other 2 electrons, and that violates the Pauli exclusion principle. This de-excitation produces a X-ray at a similar or a de-excitation energy at a similar energy as the charge non-conservation that you can see here. And we were able to set a world-leading limit for this process in leptons. And this parameter here represents essentially a ratio of how often we see this process. And then the type 1 is when a newly introduced electron, so in this case, we're using an electron that's produced by pair production, falls into the innermost orbital. So we have a lot of pair production events from our calibration data. So here you can see the single and double escape peaks produced. And the de-excitation produced here is going to produce a little echo peak offset from these by about 10 keV, which we didn't end up observing, but we were once again able to set a world leading limit for leptons. Next, I'll talk about another exotic process of multinucleon decay. So proton decay is actually something people have been looking for a very long time. That was actually the original purpose of the Super Kamiokande experiment. But there are certain models that actually forbid proton decay but allow multinucleon decay, where multiple nucleons will decay at the exact same time. So in this case, we're looking for three decays in nucleons inside of germanium. So the detection signature is going to be an extremely high energy event from the nucleon decay. So this is going to rail our detectors. And then shortly after, we'll see a nuclear decay from the daughter isotope. And based on this, we were able to set world-leading limits for all of these, although they're actually, we searched not just in germanium-76, but other isotopes of germanium as well. And this one on the archive just a few months ago. And the last one I'll talk about is what we're currently in the process of doing, which is searching for the decay of the 180 metastable state of tantalum, which is the longest lived isomeric state that we know of. So this is caught in a really unique spin trap where basically it has this low-lying spin 9 state that is forbidden from decaying into these others and ends up with a very, very long decay half-life. So we're able to search for this by installing about 17 kilograms of tantalum plates, which you can see here, and putting them in between the detectors in our detector array. And in these plates, there's 2 grams of the 180 metastable state. So this state can decay in a lot of different ways, and this diagram here can kind of shows the different ways this can happen. And we were able to search for all of them based on some of the de-excitations that are associated with those decays. This here is then showing the results. Majorana was able to set the best limits to date. The main reason is just because we had a lot more mass, but we also had very good efficiency since we were able to put the plates in between our detectors and get a very good solid angle. So the beta mode here and the internal conversion mode actually had limits that are not that far off from predictions by theory. And since we're still taking data, we're hoping we might have a chance at actually seeing these. So over here, you can see the where the peak should lie. So these little blue bands are what we're looking for. And I guess I should say that this is based on about half the data we took. This was published almost 2 years ago now. And we're still operating. We expect to stop operating later this year, and that's going to give us our final result. One really interesting thing you can actually take from this is a search for some pretty exotic dark matter models, including strongly interacting dark matter and inelastic dark matter, where basically, in order to see them, you want to sort of have the energy kick from this de-excitation. So based on the fact that we didn't see anything, we're able to set some pretty interesting limits on both of these that you can see down here. So that's all I'm going to talk about in terms of the Majorana Demonstrators physics program. I'll wrap up with a quick discussion of the future outlook for double beta decay in germanium, and then conclude. So Legend, which I mentioned earlier, is going to keep the search going. So Legend's goal is to ultimately set a half-life beyond 10 to the 28 years using some of the technologies developed by Majorana and Gerda. It's an international collaboration, mostly located in Europe and the United States, with 300 members across 12 countries. So the Legend is going to combine sort of the best technologies from Majorana and Gerda. So from Majorana, we're going to take some of these radio pure components and low noise electronics. We're going to combine that with Gerda's biggest innovation, which was dunking the detectors in liquid argon, which acts as an active shield. So it actually lights up when, say, a gamma ray goes through, interacts with a shielding, which lets us actually reject a lot of events. So the events that made up our background that I showed you before, those would have been rejected with this liquid argon veto. And both of the experiments also had a lot of other developments, including the bigger detectors, the fabrication techniques, and the control of surface exposure. And these were also the two experiments with the lowest background and best energy resolution. So the fact that they were complementary means that we can get improvements with some of these already demonstrated technologies. So Legend 200 is already operating. You can see a photo of it outside of its cryostat right here with all of these detectors. You might actually recognize some of these ones, which came from Majorana. It's operated for about a year so far, and as I said before, we're going to present a first result very soon. The next phase of the experiment is Legend 1000. That's going to ultimately have a ton of detectors. This is a drawing of what that's going to look like, and it's currently in the design phase. So finally, I'll just conclude by saying that the Majorana demonstrator, we've been operating for 10 years, and in that time, we're very proud of the science that we've been able to produce. So we produced high quality neutrino double beta decay search, as well as excellent searches for other physics beyond the standard model. And we're still operating, and we still have some results in our system. So I'd like to thank everyone for listening and ask if anyone has any questions now.
Very good. Thank you very much, Dr. Gwynn. And congratulations to you and the entire Majorana collaboration on the demonstrator's rich science program and the exciting future that you outlined with Legend 200 and the full ton scale Legend. So we can open the floor to questions. Let me see if I have any in Q&A. There was one on site at SURF in the ENO conference room. I don't know if that one wants to get asked again or not.
Yeah, I have a question. Is there any evidence of a single beta minus decay or beta decay that did not produce a neutrino?
No. So that it's harder to come up with physics theories that produce that. And the reason for that is actually conservation of angular momentum. So since these are all spin 1/2 particles involved in the beta decay, if you were to produce an electron without a neutrino, you'd actually have to change angular momentum by plus or minus 1/2. So, basically that involves a more, radical change in physics than neutrinoless double beta decay. So we tend not to look for that.
Good question. All right. Maybe I'll jump in here with one. You mentioned that you're doing or planning a combined analysis, the demonstrator, Gerda, and Legend 200. Do you have, I don't want to put you on the spot, but do you have an expectation for the sensitivity that you would reach for that analysis and maybe a follow-on? Are there implications to the excited state analysis that you showcased as well?
Um, I'll start with the neutrinoless double beta decay. I actually we haven't submitted the paper for it, but we actually did present the analysis during the neutrino conference last summer. So the sensitivity ended up being close to 3 times 10 to the 26 years. And I guess I'll shock everyone by saying we still haven't seen it. You probably would have heard if we had. For the double beta decay to excited states, there's actually, let's see, I'm going to go back a little bit. So this is actually going to be a challenging search for Legend. So at least using the detection signature that I've laid out here, where you require a gamma to go from one detector to another. The reason for that is that in Legend, there's going to be liquid argon between these detectors that will shield this gamma from going all the way. This was actually a challenge for Gerda as well. And one of the main reasons that Majorana was able to set a more sensitive limit is that this liquid argon veto system was reducing their efficiency relative to what we had for Majorana. Um, so uh, Yeah, we haven't quite run all of the simulations needed to project what we can do with this detection signature, but I think it's going to be hard to make at least substantial improvements over the Majorana results without developing some new techniques. Um, but I think there are a few things we can do. So by using the pulse shapes, we can actually probably get some really useful information for this search. In particular, we might be able to start using events where the gamma doesn't have to fly from one detector to another, but gets absorbed in the same detector. Another interesting thing we can try to do is, these gammas could interact in the liquid argon outside of the detectors. So if we're able to use some of that information as well, that might also enhance this search. So there are people thinking about that, but I think we need to see what's going to work and see how good of a sensitivity we can ultimately get.
Ian, this is Steve Sekula from Snow Lab. Just a quick question for you. I'm glad you're on slide 34. Could you go to slide 35? All right, sorry, I lied, 36. Okay, yes. So you have a world leading limit at 1.5 times 10 to the 24 year. You expected, however, to exclude more, if I'm understanding that lower right box, which implies that you had some amount of excess in the signal region. Can you comment on the size of that excess and the range of the sensitivity predictions? In other words, like a profile likelihood method where you look at the range of possible confidence limits from background.
Yeah, so I don't think I included a backup slide for this, unfortunately. But you can actually see that, I mean, this is the 90% upper limit that we got here. And I think this count here kind of shows you the excess. It more or less corresponded to, I think, less than a one count excess compared to what we expected. Maybe one count, I forget exactly. But yeah, that's what ultimately, kept us from reaching our sensitivity. Did that answer your question?
Yes, it did. And to your point earlier, like if it had been more of an excess than maybe one event, which may not be as exciting as I was hoping it would be.
Yeah.
It would have been nice to find a path for a future program to reproduce this measurement with more sensitivity, but maybe it's not on its own that compelling given the size of the excess.
Yeah, right. Yeah. So yeah, and I think, I described it just now as a background excess, but we don't know. It could actually be the start of a signal showing up, and we just need more statistics to really confirm it, and have the confidence to call it a discovery. So right now we just can't say anything conclusive.
No, this is very nice. Thank you.
Thanks, Steve. Other questions? Maybe one quick one before we wrap up. All right, I'll ask a quick one before we wrap up. The current tantalum campaign you mentioned will wrap up later this year involves natural germanium detectors. What's the plan? Will those detectors be used in some other experiment? Any thoughts on that?
Yeah, so those detectors, I believe they all belong to Los Alamos. I think they're going to take some of them back. I don't think we have plans for all of them yet, though. So I think, I don't really know for sure what we're going to be using them for yet, but they're actually very, one really nice thing about these detectors is since they've been underground for such a long time, they actually have, basically all of the cosmogenic activation from when they were on the surface. A lot of that has decayed away. So these detectors actually could be very useful for underground science. And I believe that the Los Alamos crew is planning on continuing to keep them underground over there as well.
Sure. Yeah, no, clearly with the slide you're on here, the tantalum campaign is doing great science with those experiments. You have a well-characterized array of germanium detectors, a fabulous shield, and it's great to see additional results come from that setup.
Yeah, I'm very excited to see what our final result is for that.
Yeah, no, we're fingers crossed. All right. Well, with that, let's go ahead and wrap up. This talk, as I mentioned at the top, is available to view and share on YouTube, Vimeo, and on our Institute website, institute.serve/deepertalks. Next month's Deeper Talks will be on April 9th at 9 a.m. Mountain Time, and the topic is scaling permeability evolution driven by seismicity. with featured speaker, Dr. Derek Ellsworth. Your feedback helps improve this program, and we appreciate any suggestions for speakers and topics for future talks, and we've received a number of those. Thank you for providing that feedback. At the end, once we sign off, there will be a short survey following the talk on Zoom and in your email. So with that, we will sign off. Thank you once again for joining us, and hope to see you at the next event.
Thanks, everyone, and thanks for the good questions.